Hello. We at the Mr. CFD Group are honored to present you with training services. In this concepts chapter, we aim to introduce the electrolysis model in ANSYS Fluent software. We intend to provide a comprehensive background of the electrolysis process and introduction of various electrolysis models. Please stay with us. We want to have a general introduction to electrolysis processes. But before that, we recommend that you get to know fuel cells. In simple words, fuel cells are energy converter devices that convert the chemical energy of fuel into electrical energy. Electrolysis processes are the reversed operating process of fuel cells. In other words, electrolyzers are the reversed fuel cells. So, electrolyzers are devices that convert electrical energy into chemical energy. That is, electrolysis processes are used for the production of hydrogen as a secondary energy carrier. Hydrogen production processes in electrolyzers occur in different methodologies. That is, there are several types of electrolysis, including high-temperature electrolysis, PEM electrolysis, and alkaline electrolysis. We aim to introduce modules corresponding to electrolysis modeling in ANSYS Fluent software. Note that the various electrolysis models are available in the Fluent software environment. For example, the high-temperature electrolysis model is available in the fuel cell and electrolysis module. Meanwhile, PEM and alkaline electrolysis models are available in the potential electrochemistry module. In all different electrolysis models, two electrochemical reactions take place. During these electrochemical reactions, water is converted into hydrogen and oxygen. However, the main difference between different electrolysis models is due to their electrochemical reactions. In other words, the electrochemical reactions in different electrolysis models are not similar. For example, in high-temperature electrolysis, in the first step, water vapor splits into oxygen ions and hydrogen, and in the second step, oxygen ions convert into oxygen. In PEM electrolysis, in the first step, water splits into hydrogen ions and oxygen, and in the second step, the hydrogen ions convert into hydrogen. In alkaline electrolysis, in the first step, water splits into hydroxide ions and hydrogen, and in the second step, hydroxide ions convert into oxygen and water. To gain better insight into the operation of an electrolyzer system, we need to describe the configuration of an electrolyzer and its components. Here we present a schematic of the configuration of an electrolyzer. The overall construction of an electrolyzer is similar to a fuel cell. Electrolyzers consist of two main parts, including anode and cathode. These anode and cathode sides are connected through an electrolyte layer. Each of the anode and cathode sides consists of several layers and channels. They include the current collector, flow channel, porous electrode layer, and catalyst layer. These are the main components inside all fuel cells and electrolyzers. In addition to the main components, cooling flow channels are also used in some electrolyzers. Note that these cooling channels are optional components. Water flows inside flow channels. Depending on the electrolysis model, the water flow enters from the anode flow channel or the cathode flow channel. The porous electrode layers diffuse the water flowing in the channels towards the catalyst layers. Since the porous electrode layers are composed of porous medium, they are known as porous electrode layers. The catalyst layers are where electrochemical reactions occur. That is, catalyst layers lead to the increasing rate of electrochemical reactions. These catalyst layers are also composed of the porous medium. The required electrons to participate in electrochemical reactions are supplied through the external electrical circuit. These electrons are transferred to current collectors. That is, these solid collectors are where the electrons are collected. Again, we refer to the anode and cathode catalyst layers where electrochemical reactions occur. In these electrochemical reactions, electrons are consumed and ions, or the protons, are produced. Note that since electrolyzers are power-consuming devices, electrons are consumed in the reaction with water. The electrons are conducted in solid layers. It means electron conduction occurs through solid current collectors and solid grids of the porous electrode and catalyst layers. Meanwhile, the produced ions are conducted in the electrolyte layer. It means ionic or protonic conduction occurs through the electrolyte membrane layer. So, in electrolysis systems, two potential equations are solved. A potential equation is related to the electron transport in the solid zones of different layers. Hence, this potential is called phi sol. The other potential equation is related to the ions transport in the electrolyte membrane layer. Hence, this potential is called phi mem, where sigma is electrical conductivity in solid zones and ionic conductivity in fluid zones, while R is the volumetric transfer current. In addition, the subscripts sol and mem represent the solid phase and membrane phase, respectively. Note that the difference between the solid phase potential and the membrane phase potential is equivalent to the surface over potential, which indicates the driving force behind the electrochemical reactions. Since the two potential equations are solved throughout the computational domain, we need to define the boundary conditions in terms of phi sol and phi mem. No ionic current leaves any of the external boundaries of the electrolyzer. In other words, the ions produced by electrochemical reactions don't pass the external boundaries of the electrolyzer. Therefore, for all external boundaries of the electrolyzer layers, we use the potential flux condition so that we define the ionic potential flux as equal to 0. But unlike ions, electrons can pass through the external boundaries of the electrolyzer. In other words, the consuming electric current is transferred to the electrolyzer through the external boundaries of current collectors. These external boundaries of the anode and cathode collectors, called the anode and cathode tabs, are in contact with the electric circuit. Therefore, for these external contact boundaries, we use the non-zero potential value condition or non-zero potential flux condition. Note that the fixed potential value indicates the voltage of the electrolyzer, while the fixed potential flux indicates the current density of the electrolyzer. Electrons pass only through external boundaries in contact with the electric circuit. So for the other external boundaries of the electrolyzer layers, we use the potential flux condition, so that we define the electric potential flux as equal to 0. After describing the boundary conditions corresponding to the solid and membrane phase potentials, we return to the two potential equations presented moments ago. As we said before, the source terms in the potential equations are equivalent to the transfer currents on the anode and cathode sides. Note that each source term of the R sol or R mem includes both Rn and Rcat source terms. These source terms, also called exchange current densities, are defined on both the anode and cathode sides by these relations shown, where Jref is the reference exchange current density per the active surface area, and delta is the specific active surface area. Alpha is the transfer coefficient, and F is the Faraday constant. Bracket and bracket ref are equivalent to the local concentration of the desired species and the concentration of the desired species at the reference state, respectively. In simpler words, bracket A indicates the molar concentration of the flowing species in the anode side of the electrolyzer, and bracket C indicates the molar concentration of the flowing species in the cathode side of the electrolyzer. For example, if water only flows in the anode side, bracket A is assumed to be equal to H2O concentration and bracket C is assumed to be equal to unit. W is local surface over potential, also known as activation loss. As we said moments ago, the surface over potential is equivalent to the potential difference between the solid and the membrane phases. Note that by crossing from the anode side to the cathode side, or vice versa inside the electrolyzer, the electric potential increases. This gain in electric potential is accounted for by subtracting the open circuit voltage on the anode or cathode side. In electrolysis processes, there is current conservation. Since the electric current produced on the anode and the cathode sides of the electrolyzer are the same, the current conservation relation is expressed as shown. In addition to the current conservation, there is also mass conservation in electrolysis processes. For maintaining mass conservation in the electrolysis process, a series of volumetric source terms appear for species participating in electrochemical reactions. This volumetric source terms for O2, H2, and H2O species are expressed as shown, where MWH2O, MWH2, and MWO2 represent the molecular mass of water, hydrogen, and oxygen, respectively. Also, F is equivalent to the Faraday constant, and numbers 2 and 4 indicate the number of electrons per mole of reactant or product. Depending on which side of the electrolyzer each species flows, Rn or Rcat is used in the relations of source terms. In addition, since the water is consumed in the electrochemical reactions of the electrolyzer, a negative sign is applied to the relation of the H2O source term. However, since hydrogen and oxygen are produced in electrochemical reactions, the positive sign is applied to the relations of the H2 and O2 source terms. In the electrolysis process, the energy equation is also solved. In this energy equation, a series of additional heat source terms are applied to the energy equation. In other words, during the production of oxygen and hydrogen in electrolyzers, not all electrical work is converted into chemical energy. Hence, these additional heat source terms appear in the energy equation. These heat sources are applied to the computational domain of different layers of the electrolyzer. The base relation for defining the heat terms due to the electrolysis process is equivalent to dividing the second power of the current density by the electrical conductivity. However, in the catalyst layers, where electrochemical reactions occur, more heat terms appear. Where IS and IM represent solid phase current density and membrane phase current density, respectively. Sigma S and sigma M represent solid phase conductivity and membrane phase conductivity, respectively. Rn and Rcat represent the transfer current on the anode side and the transfer current on the cathode side, respectively. Wn and Wcat represent the surface overpotential on the anode side and the surface overpotential on the cathode side, respectively. Delta An and delta Cat represent entropy changes on the anode side and entropy changes on the cathode side, respectively. Also, N represents the number of electrons involved in electrochemical reactions. So far, we described the overall operation of an electrolyzer and all the governing relations in the electrolysis process. Now, we intend to introduce 3 different models of the electrolysis process in ANSYS Fluent software individually and comprehensively. These electrolysis models include high temperature, PEM, and alkaline. First, we describe high temperature electrolysis. In the high temperature electrolysis, power is supplied to convert water vapor into hydrogen and oxygen. In these electrolyzers, high thermodynamic efficiency can be achieved only at high operating temperatures, means more than 500 degrees centigrade. For this reason, the flow field exists only in the vapor phase. Now we describe the operating mechanism of high-temperature electrolysis. Water flows in the channel on the anode side. Also, since electrolyzers are power-consuming devices, electrons are supplied from the anode collector side through an external electrical circuit. In high-temperature electrolysis, 2 electrochemical reactions occur in the anode and cathode catalyst layers. In the catalyst layer on the anode side, water reacts with electrons to produce oxygen ions and hydrogen. Oxygen ions are transferred from the anode side to the cathode side through the electrolyte layer. Then, in the catalyst layer on the cathode side, oxygen ions split into oxygen and electrons. Next, we describe PEM electrolysis. The PEM electrolysis provides the modeling of the polymer electrolyte membrane layer. It means that the polymer electrolyte membrane layer is used to transfer ions between the anode side and the cathode side. Also, in the PEM electrolyzer, liquid water is present at an operating temperature of about 60 to 90 degrees centigrade. Now we describe the operating mechanism of PEM electrolysis. Water flows in the channel on the anode side. Also, since electrolyzers are power-consuming devices, electrons are supplied from the cathode collector side through an external electrical circuit. In PEM electrolysis, 2 electrochemical reactions occur in the anode and cathode catalyst layers. In the catalyst layer on the anode side, water splits into hydrogen ions, oxygen, and electrons. Hydrogen ions are transferred from the anode side to the cathode side through the electrolyte layer. Then, in the catalyst layer on the cathode side, hydrogen ions react with electrons to produce hydrogen. Finally, we describe alkaline electrolysis. In alkaline electrolysis, alkaline mediums are used. Also, in alkaline electrolyzers, liquid water is present at an operating temperature of about 60 to 90 degrees centigrade. Now, we describe the operating mechanism of alkaline electrolysis. Water flows in the channel on the cathode side. Also, since electrolyzers are power-consuming devices, electrons are supplied from the cathode collector side through an external electrical circuit. In alkaline electrolysis, 2 electrochemical reactions occur in the anode and cathode catalyst layers. In the catalyst layer on the cathode side, water reacts with electrons to produce hydroxide ions and hydrogen. Hydroxide ions are transferred from the cathode side to the anode side through the electrolyte layer. Then, in the catalyst layer on the anode side, the hydroxide ions split into oxygen, water, and electrons. After describing all types of electrolysis models, we aim to train how to simulate these electrolysis models in the ANSYS Fluent software. As we said before, it is possible to simulate these types of electrolysis processes by the Fuel Cell and Electrolysis module and the Potential Electrochemistry module in ANSYS Fluent software. First, we introduce the Fuel Cell and Electrolysis model. As you see, the Fuel Cell and Electrolysis module is enabled in the Models panel in the Fluent software environment. Note that the Fuel Cell and Electrolysis model is an add-on module. It means that the Fuel Cell and Electrolysis model is not available by default in the Fluent software environment, and hence, we need to load it in the Fluent software. Therefore, we write a command code in the console panel of the Fluent software. This command code includes define, models, add expressions. After writing this command code, a list of add-on modules will be displayed in the console panel. Therefore, we write the number 3 so that the fuel cell and electrolysis will be activated. We open the setting panel of the fuel cell and electrolysis model. In the first step, we turn on the Enable Fuel Cell model. Then, step by step, we check the different setting tabs of the fuel cell and electrolysis panel, including models, parameters, anode, electrolyte, cathode, and reports. First, we go to the Models tab. As you see, we can simulate both PEMFC and SOFC fuel cells and simulate electrolysis. So we select the electrolysis option, which indicates high-temperature electrolysis. Next, we go to the Parameters tab. Here we can determine the variables used in the relations governing the electrolysis process. Next, we go to the Anode tab. Here we define the different layers of the electrolyzer on the anode side, including the anode current collector, anode flow channel, anode porous electrode layer, and anode catalyst layer. Next, we go to the Electrolyte tab. Here we define the electrolyte layer of the electrolyzer between the anode and the cathode sides. Next, we go to the Cathode tab. Here we define the different layers of the electrolyzer on the cathode side, including the cathode current collector, cathode flow channel, cathode porous electrode layer, and cathode catalyst layer. Finally, we go to the Reports tab. Here we define the anode and cathode tabs in the electrolyzer. In other words, we specify the terminals connected to the external electrical circuit. Then we introduce the Potential Electrochemistry model. As you see, the Potential Electrochemistry module is enabled in the Models panel in the Fluent software environment. We open the setting panel of the Potential Electrochemistry model. In the first step, we turn on the potential equation and select the electrolysis model. Then, step by step, we check the different setting tabs of the electrolysis model panel, including models, parameters, anode, electrolyte, cathode, and electrical tabs. First, we go to the Models tab. As you see, we can simulate both PEM electrolysis and alkaline electrolysis, so we choose the type of electrolysis process. Next, we go to the Parameters tab. Here we can determine the variables used in the relations governing the electrolysis process. Next, we go to the Anode tab. Here we define the different layers of the electrolyzer on the anode side, including the anode current collector, anode flow channel, anode porous electrode layer, and anode catalyst layer. Next, we go to the Electrolyte tab. Here we define the electrolyte layer of the electrolyzer between the anode and the cathode sides. Next, we go to the Cathode tab. Here we define the different layers of the electrolyzer on the cathode side, including the cathode current collector, cathode flow channel, cathode porous electrode layer, and cathode catalyst layer. Finally, we go to the Electrical Tabs tab. Here we define the anode and cathode tabs in the electrolyzer. In other words, we specify the terminals connected to the external electrical circuit. We conclude that we can simulate different electrolysis models in ANSYS Fluent software, both by the Electrolysis submodel in the Fuel Cell and Electrolysis module and by the PEM electrolysis and alkaline electrolysis submodels in the Potential Electrochemistry module. However, what is the difference between the Fuel Cell and Electrolysis module and the Potential Electrochemistry module during the simulation process of electrolysis? The simulation process of electrolysis models in the Fuel Cell and Electrolysis module and the Potential Electrochemistry module are very similar. However, the main difference between these two modules is how to define the electric potential on the anode and cathode sides of electrolyzers. For example, in the fuel cell and electrolysis model, the electric potential on the anode side is considered zero, and the electric potential on the cathode side has a non-zero value. Meanwhile, in the potential electrochemistry module, the electric potential on the cathode side is considered zero, and the electric potential on the anode side has a non-zero value. Thank you very much for being with us. I hope you are satisfied with our training. The Mr. CFD Group will always be ready to provide you with training services.